You all were so good at that. Well done. Well done. We were like, oh, are we going to have to walk around and like make sure they're actually mingling? No, I didn't have to do anything. You guys were great. Hopefully you found that fun. So next, I would like to introduce Nick Wu to come up. And Nick is at Imperial, and he's going to tell us things about effects. And it's going to be great.
Cool. Okay, good, great. Okay, well, thanks for the invitation to talk about this stuff, and it's great to see so many of you here, so well done for making it, and well done for being so brave to talk to one another. That's something that I don't think I would be able to do. Today's talk is about the evolution of effects, and my goal here is to give you a talk that's not actually technical, it's actually more historical. And what I'm trying to highlight throughout this talk is the degree to which innovation happens in lots of small steps over a very long period of time. And hopefully you will all become part of that tiny evolution of what humans get to know. Okay, so the story is about effects, and it's basically a brief history, and it starts with programming language in the large, moves on to something called monads. I'm curious, who knows what a monad is? Great. And then we talk about these things called effect handlers, and then I'll be talking about higher order effects, which is the stuff that I've been working on. And so the caveat is that there's just too much to history for me to even nearly cover everything, and I will make mistakes, and I will make omissions, and so this is just difficult. Right, so the story starts with functional versus imperative programming, and functional programming inhabited by Alonzo Church in the early days, and his PhD student, Alan Turing. And it's really fun because, of course, Alonzo Church says, the way to do computation is to use the lambda calculus, and Turing says, no, we want to be using assignment statements instead. And so right from the beginning of computer science, really, we see this tension between the two. And so my research has been trying to resolve this tension. So I laugh because I'm the head of the functional programming group, except all we end up doing is imperative programming all of the time because we're just trying to deal with effects. So there's that. So I'm going to just start with a brief history of programming languages. And because we're in London, let me take you back to London in 1666, and London is burning. So there was this fire that started off in some bakery, and much of London got destroyed, and people drew beautiful pictures of the event. What also happened in 1666 is this man called Leibniz finished his PhD thesis, and his PhD thesis was the art of combinations, or combinatoria. And what did he do in that work? Well, he extended, he basically talked about a proof of the existence of God from various axioms, and he decided that what was important was to have a kind of an alphabet of all human thought so that he could combine the ideas so that you could talk about ideas and combine them into larger ideas and argue about them formally and semantically. So that was an important piece of work. Because again, we're in London, one of the ideas that he had was he said when he was trying to get from England to Holland, he was detained for some time in the Thames by adverse winds, can you imagine? During that time, knowing not what to do and having nobody in the ship except sailors, I meditated on things and especially thought about my old design of a rational language. See, he's a PL person from the beginning. And for if we had such as I imagine, we could reason about metaphysics and morality just like we do about geometry and analysis. And that was a letter from him to Galois, a different Galois, in 1677. Okay, so he was a programming language designer. A little bit later on at a conference, there's a keynote where this guy, Dubois-Reymond, says, ignoramus et ignoramibus. We do not know and we shall not know. So he's talking about the sum of human knowledge and how there's just too much to know in the first place, and actually certain things that we just won't be able to. Well, slightly later on, Hilbert, at the same conference, also gives a keynote, and I think gives a response to what was said before. And he says, wir müssen wissen, wir werden wissen, we must know, we shall know, in defiance. Well, is that how things turned out? In 1928, Hilbert and Ackermann formalized the decision problem, the idea that given an input and a first-order predicate statement, was there a way of always determining whether there was an answer yes or no to that particular problem? We shall know was the thing that he wanted to know. But in 31, Gödel, of course, gave us the incompleteness theorem, and that told us that actually there was no system of logic that could be proven to be complete in this sense. But maybe there'd be some way of having an algorithmic system that would be able to break that. Maybe algorithms were the solution. And of course, we get two independent results by our friends Turing and Church saying actually no such algorithmic procedure is possible. And they do that from very different perspectives, one by building the Turing machine and running some tapes through, and the other one by proving limitations of what can be expressed mathematically in the lambda calculus. Okay, so Turing machines were in the air, the war breaks out, and von Neumann was a really big name at the time. Von Neumann was in charge of basically building a computer, and so started the so-called von Neumann architecture, which is very much what our computers are based on now. So you've got a store and you've got registers, and instructions are passed through these things. And so he was very much in charge of the EDVAC in 1949. History of computing, or computers, sorry, is actually very complicated to get right. There was also the EDSAC, which was the British version, made in 1948, slightly earlier than the Americans. But actually, there's lots of controversy about what came first and which is the right machine. And then there are even earlier machines in this, and what is a computer, and blah blah blah. So I'm not going to go into any of that, right? But the point is that these machines became the beginnings of programming itself. So rather than having lots of instructions, Backus basically said, I'm tired of writing in assembly. I think I would like to write things in a higher order language, in a human language. And so he says, much of my work has come from being lazy. I didn't like writing programs. And so while I was working on the IBM 701, basically he made up a programming language. And so he says that most people think that the main contribution of Fortran was to be able to write algorithms in terms of formulae. But actually, for him, it was the organization of loops. So I think this is an interesting point because we often think of programming as making specific statements, but actually programming is very much about control flow and trying to organize that, which I think is quite an insightful thing that he's saying here, because actually when we get into the idea of effects, the hard part is not so much all the algebraic evaluation. It's not the part that's sort of mathematical. It's the control flow that's the difficult thing. So this is exactly what in agreement. Okay. At around about the same time, or very little bit later, you've got this programming language called Lisp. I'm curious, who knows of Lisp at least? Okay, I think most people. Good. Okay, that's good. They still teach things in school. So Lisp is a very early language. Basically, the idea was that it was an implementation, in some sense, of the lambda calculus. And he introduced things like the conditionals. So when you use an if-then-else statement, that was originated by McCarthy. That you should not call them if-then-else statements. You should call them McCarthy conditionals. And he introduced recursive functions, at least recursive functions mechanically in this language, and Lisp processing. But rather than having head and tail, he called them car and cudder, right? And higher order functions were there. So we can see conditionals being expressed here in his paper. Where he's saying it's a good idea to have pattern matching and to cover your cases. And bear in mind, this is in 1960. He also has this function here. I'm sorry it's so small, but it says map list xf equals if it's null, then do nothing. Otherwise, if it's this thing, do. So this is exactly the mapping function that you would find in Haskell. And the car and cudder thing is quite funny because that has more to do with the registers in the IBM machine where you would find the head and the tail of the list. So we're talking about lists in terms of pointers here. And he also coined the word abstract syntax in '62. So I think a lot of what we're going to see in this talk is it feels like everything was invented in the 60s and 70s. But my point is it wasn't invented in the 60s and 70s. They had a green field to start with, and they came up with lots of the original concepts, which we've been refining ever since. And so your job is not to come up with new concepts from the ground up like they did, because they had it easy. Your ideas will be to just improve things incrementally towards something better, right? That's the goal. Okay, you might get lucky, but Okay, so in '58, these two characters, Backus and McCarthy, amongst a whole bunch of other people, like Peter Noir, invent this programming language called Algol. Now, Algol is probably the first proper programming language after the previous two, but it was actually a very special language because it looks very much like imperative programs today. And Tony Hall remarked that it was a language so far ahead of its time that it was not only an improvement on its predecessors, but on also nearly all its successors. And so there's some truth to that in the way this language was. There was iteration and recursion. There was distinct assignment versus equality. Code blocks and lexical scope came into this. We had nested procedures, procedure passing, BNF, call by value and call by name. All of these things came with Algol. I mean, it's phenomenal that they had so many ideas in one go. I didn't put the slide to it, but there's a funny picture of the way this of the committee that designed this language, where they're all putting their hand up. It's a nice black and white photo where you can see the group, and apparently that is the only time when the entire group agreed on anything at all. And the question that was asked to them when they all put their hands up was, do you agree to have your photograph taken? All right. In '64, we get this this chap called Peter Landin. So Peter Landin wasn't part of the Algol committee, but he made some really huge contributions towards its development nonetheless. So one of the things that he did was he wanted to think about how you could mechanically evaluate expressions. So by expressions, we're talking about what he called applicative expressions, and they are, they almost look like Haskell, where you've got let statements and where you have mutually recursive functions, mutually recursive definitions separated by the and keyword. And his idea was, we want these applicative expressions to be basically like surface syntax for the lambda calculus, and we need a way of being able to evaluate these expressions in an actual machine. So how do we need that? How do we do that? Well, we need some kind of abstraction for what the machine is. What's that going to be? Well, it's this thing called the SECD machine, which has a number of different stacks for evaluation, control, and dump. So basically, these interacting components are quite easy to implement in a real machine, and they also can be proven to be a useful sort of substrate for the lambda calculus to execute as well. So this was a very big landmark paper. It's also the paper where indentation sensitivity was first introduced to programming languages. So that's quite fun. And there's something else as well. I forget. So there's something else that's original in this paper. Anyway, there are lots of things that are original in this paper. Right. And then in '65, so 1 year later, he extends the applicative expressions language, AE, into the imperative AE, which is where he adds assignment operations to it. And then using imperative AE, he shows a correspondence between Algol and IAE, and then that's how he gives the semantics to Algol. And actually, you can think of this as being the first times anybody did denotational semantics in computer science. Because denotational semantics is this idea that in order to give a semantics, well, let me just take you back a little bit first. Some of this you will definitely know, but the SECD machine description is basically an operational system that says, here's how the machine moves from one state to the next state. So that's operational semantics, describing things in terms of steps. If you go back to Turing's description of Turing machines, that's an operational semantics. It tells you how the Turing machine moves from one state to another in progressive steps. But actually, even if you look at Alonzo Church's work, he's talking about like beta reductions, which is also an operational semantics for the lambda calculus. So at this point in time, we only have operational semantics. What Landin does is he says, look, the way we should understand Algol is by translation into another language that we already understand. So we already understand the imperative applicative expressions, and that translation is the semantics of Algol. So denotational semantics is about starting with some syntax and saying that the mapping from that syntax to some mathematical object itself is the semantics of that. So we see an early version of this, and then I think something like 2 or 3 years later, we get the work by Scott and Strachey, which shows how denotational semantics can be done formally and mathematically. But anyway, I think it starts with Landin. Landin is known for another paper which is quite famous, which is called The Next 700 Programming Languages, which was written in 1966, where he already foresaw that programming language programming languages were going to just explode in complexity and the number of languages they were. Again, even in the 60s, the number of languages in development was actually quite huge. Everybody was making their own up. So he invents or introduces ISWIM, which stands for "If you see what I mean." So there was a kind of a movement in the 60s to having acronyms for every single programming language that you invent, and so that's what he had as his. And the way he understood ISWIM was that this should be church without lambda. That was the subtitle for his talk, for his paper, and actually. It's a paper that encapsulates or more formally introduces a language that he'd been using for a couple of years. So even in the mechanical evaluation paper that we just talked about, he's already using something that is in essence like ISWIM. But there are some details that he wants to introduce here. This was a Haskell predecessor, which had things like pattern matching in it, where clauses, garbage collection, and indentation, of course. So, that's a lot of features for 1966. The catch is that it was never actually implemented. It was completely a pen and paper language for a very long time. But to give you some snippets of what it looked like, this could be Haskell. So the stuff on the left-hand side is the ISWIM code, and the stuff on the right-hand side is how he would translate that into the lambda calculus. There's a really funny, at the end of this paper, there's an interesting sort of transcription of the discussion that happened after his talk, and it's really worth reading that because you get an insight into what the big names at the time, how they were thinking. And actually, what's fascinating is that the kinds of questions that they ask and the discussions that they have, they're not all that scary. Actually, these guys were just still discovering what computer science was all about from the ground up. And so, anyway, we've got this comment from Peter Noir who says, regarding indentation, in many ways, I'm in sympathy with this, but you would regret it because of the kind of rearrangement of manuscripts done in printing. I mean, is that really the kind of comment that you make? Well, that's where they were at the time, in certain regards. This was a time, you have to remember, before LaTeX, where putting things in print together was not easy. It's not become any easier. One of the key things of ISWIM is that it was equipped with equivalences for reasoning. And by that, basically what Landon did is he identified 4 different categories of things that we would want in his core language that enabled reasoning to happen within the program itself. So he thinks that there should be equations that tell you how sub-expressions should work. So basically, if you've got 2 terms that are equal to each other, then those 2 terms should still, then if you have a function on those 2 terms, then they should still be, the output should also be equal. So this is actually just an application of Leibniz law, which was obviously a lot before that. But he thinks this is something that we should be thinking about in programming languages. The equivalences themselves are essential. Then he thinks about definitions, and there should be equivalences within definitional forms as well. By that, he's saying that the user should be able to write equivalences, that's to say definitions of functions and variables, and be able to do that in multiple ways. So he wants let statements and he wants where statements in this language. And he thinks it's right to have different ways of expressing yourself. And the way that you say, well, these things are equal is by using inequality. Surprise, surprise. But the point is that at this time in history, these things weren't obvious. It wasn't obvious to say that this is how we should define languages at all by using mathematical equivalences. So I think one of the things that strikes me is all of these discoveries over this long period of time, they feel to us like, how could you do this in any other way? But actually, it's the kind of thing where it's easy in retrospect. And a lot of the papers that I write are sort of the kinds of things where I think, well, that wasn't so hard. Well, in retrospect, it wasn't very hard, but actually doing that was difficult. And so I find it very easy to sort of go, well, I'm not really sure if my research is any good at all, or if I've actually contributed anything to the world. I probably haven't. But then if you look at it, you're like, well, actually, no, it was actually quite hard at the time. It's just that now that I look back on it, it's not so much. So I guess, without trying to offend you, I think we're dumber than we think. And that's okay, right? That's how humanity progresses in small increments as we go. Okay, The next thing that he wanted to have was equalities between built-in expressions. So with things like if-then-else statements, so this is an if-then-else. He says if something is true, then do m. If it's false, then do n. And he thinks, well, the way you should define built-in operations is with, well, equivalences again, okay? And then the last one is probably the one that makes the most difference in this language. Oh dear, let me just go forward again. Sorry about that. There's some funny lag between my computer and what you're seeing, I think. Okay, so the last thing that he introduces is equivalences between primitives. And I think this is probably the main contribution of this paper, and it's what the title is after. So let me try and explain this a little bit. It's called the next 700 programming languages because he thinks that up until now, programming languages have been too hemmed in the way they're described. So up until this point, a programming language is, a core language, and that's all it is. But for Landon, programming is about creating small languages, or domain-specific languages is what we'd call them now, that solve specific problems. So he calls these primitives. So the primitives are primitive to the problem that you're trying to solve. And his idea with ISWIM is that the user should be able to define their own primitives that solve particular problems. And so that's why he's saying, look, actually, if I give you a core language that can be easily extended in multiple ways, I've given you a way of creating new languages. And so that's where the next 700 programming languages is coming from. But in order to do that, it's not enough for me to just give you some programming tools. I need to give you a way of defining new expressions, so new parts of your language, new syntax. But also, I need to give you a means of defining equivalences between things within that syntax. So equality again is key. So for him, ISWIM is all about a problem orientation of ISWIM can be characterized by additional axioms. In the simplest case, it's just an ISWIM definition, and he calls these definitional extensions in his system. It's hard to quote Landon because he writes in an extremely terse way. And I think that one of the things that has happened over the course since the 60s is that we as a community have become better at writing papers. But I still think we have a long way to go. And I think one of the problems with the early writings is that they kind of assume that you already know what they're talking about. Maybe it's because there's just a vernacular that's going on in the room and everybody just understands the language and there's just an assumption that everyone knows what the problems are at the time. Perhaps that was true then. But for me, as an expert looking back into the 60s, where I have a fairly good understanding of programming languages, these papers can be impenetrable. No, they're not all impenetrable. Some of them are really easy reads, but some of them are like, what on earth is the problem that they're talking about here? What's the problem that they're talking about there? And I think this is one of those things where, as you're writing a paper, it's very easy to get lost in your own technical terminology and forget that somebody needs to actually read this, and that person might not be you. So it's great when you're writing a paper to be unafraid of bringing things back almost to first principles, making things easy to read. There's one thing that I like to say, which is it's much easier to write a paper than it is to read a paper. So try and make your papers easy to read rather than easy to write. Okay. And that's not to poo-poo Landon at all. He was like a phenomenal man. So I want to then take us towards structured programming, because where I'm trying to get you is to understand effects. And effects are basically based on a structural deconstruction of a syntax tree. So where do we go for structured programming? The beginnings of structured programming start with ISWIM in some sense, because it was a language that was useful for reasoning and thinking about structured programming in the first place. So Burstall starts thinking about how to prove properties by structural induction in ISWIM. And that's one of the early works on this. There's also work by Tony Hall then that goes into recursive data structures, but that's about 1 or 2 years later. And so in this paper, he has an early definition of the concat statement, which almost looks like we would write it today. He then starts talking about how you would have a function for sorting via flattening trees. And again, this could practically be a functional Perl that we're reading today, right? So this was very early work. And furthermore, he has a proof of its correctness by using induction. Okay, the idea of structured programming, the idea that you can make good progress by looking at some data type and then mathematically, by induction, proving properties of that thing, becomes a really big idea. And it's popularized in '72 by Dijkstra, Hoare, and Dahl in this wonderful book called Structured Programming. And I guess today it's something that it's a technique that we all know about and would use very easily. So that's one big thing. And I think the key quote from this book is that there are certain close analogies between the methods used for structuring data and the methods for structuring a program which process that data. And we continue to exploit that. One of the other things that came out of Landon's paper was actually an early denotational semantics, and I've already kind of touched on that. He makes that really clear when he says that, so there are these three clauses that he talks about for what it means to be denotational. So first, so I haven't properly highlighted that, but is this working? Oh, so there's a 2-second lag between what I'm doing and what's going on. So this is like a really difficult video game where you have to, okay, I'm not going to play this video game anymore. The point A on the slide says that each expression has a nesting sub-expression structure. If we look a little bit further forward to the 1971 paper by Scott and Strachey, you see this equation here, which is the first rendition of what it means for something to be denotational. What this says is that the valuation of the expression v0 plus v1 is equal to the valuation of v1 of v, so the valuation of v0 plus the valuation of v1. If you look at how Landon's description of things it basically corresponds to this equation. So part A says that each expression has a nesting sub-expression structure. So the expression in this case is v0 plus v1. And the nested part is that you've got a v0 and a v1 on the right-hand side. So that's the first thing that he's talking about. B is each sub-expression denotes something. So v0 should denote something, v1 should denote something. Well, on the right-hand side of the equation, you have the valuation of v0, that denotes something, and the valuation of v1, that also denotes something. And part C of what Landon is saying, he says, where is it? The thing that the expression denotes, i.e. its value, depends on the values of its sub-expressions. So the thing on the left-hand side, the valuation of v0 plus v1, should be a combination of the valuations of the things on the right-hand side. Well, in this case, it's addition. So he's exactly describing denotational semantics, but he hasn't done so using a mathematical equation at this point. That happened much later when Scott and Strachey start thinking about what domains look like and how complex all of that is. Okay. So let me kind of draw us back to this dichotomy of functional versus imperative programming. What I'm trying to argue is that from an early time, Landon saw that this dichotomy shouldn't really exist at all. That actually we can have programming languages that have both, right? So he's got the imperative applicative expression language, and he's thinking about this in terms of the lambda calculus from the go. And he says that ISWIM brings into sharp relief some of the distinctions that the author thinks are intended by such adjectives as procedural, non-procedural, algorithmic, heuristic, imperative, declarative, functional, descriptive. Well, here's a suggested classification in the new word. So what he's saying at this point is that there is this idea at the time already that there is lots of different programming styles that are not imperative. So all of these things are unimperative programming languages. But what is the thing that draws all these things together? Well, his new word is denotative. So denotative programming is the antithesis of imperative programming. So imperative programming is giving statements about how things should work, or in an operational setting, whereas denotative is giving a denotation to things. I think today we might, instead of saying denotative, we might say compositional, perhaps, but I think the ideas are essentially the same, and denotative is a perfectly fine word to describe the non-imperative things. It's funny because I gave a talk at Paddle yesterday, and so that's the practice and applications of declarative languages, and it's about declarative languages. And I thought, well, I'll give these guys a definition of declarative languages to start the talk. Let's see what people have written about what a declarative language actually is. And the definition of declarative is just not imperative. Which I think it's kind of sad, right? That we're defining a concept in terms of not this other thing. Where I think Landon is trying to be constructive here and say, actually, it's denotative. It's stuff that you can construct out of the constituent parts. I think it's a much more useful classification. Okay, so perhaps there's this sort of nice synergy between side effects and pure things going on, where you can define one in terms of the other. They're not in conflict, so I think that Landon saw that at this early time. Okay, so what this would require would be a denotative way of expressing side effects that supports reasoning, and that's what I think we get with monads. So why do we have a picture of a burrito here? Well, this has to do with internet folklore. It's because of Brent Yorgi and his post in 2009, where he explains that monads are like burritos. Actually, in his defense, he explains a hypothetical person, I think, called Joe, who thinks that monads are like burritos. I don't know whether Brent himself thinks that monads are like burritos. He assures me he doesn't. But because we're doing history, I want to take you right back. And this is South Africa in 71,000 BC. This is not a joke picture. This is actually a rock that was discovered in that region that dates back to 71,000 BC. We've got scientific papers written about this thing that shows that if you look at the inscriptions made out of ochre, they correspond to something that could only have been man-made, and this is truly the oldest thing that has been found that's been written on. Isn't it magnificent? But if you look very closely at these detailed lines that we have here, you might realize that mankind has been striving for Haskell for a very long time. Let me show you another artifact from South Africa in 71,000 BC, which is this beautiful picture of basically the Haskell committee getting together and coming up with all the ideas that they had. Actually, Haskell was very, very closely related to Miranda, which was its predecessor, and which was conceived by David Turner, and itself was very similar to ISWIM, but nevertheless, this is the committee. And there's a really lovely paper written in 2007 about a history of Haskell being lazy with class. I really recommend that you read that. And one of the sections in that paper talks about monads as input and output. So the original version of Haskell did not have monads in it. So there was no way of doing I/O in the way that we do it now. What they did have was I/O as being done through streams. So the idea is that Haskell is a lazy programming language, and you can have a stream of input, which is all the input that the user will give you, even the stuff that's in the future. And as you demand that stuff, well, maybe it will arrive, but if you keep on waiting, eventually something's going to come down on this stream, which will be the input that comes from the future. And then what you need to output back out is this infinite stream of things that your program does. And so you've got this, these two streams of requests and responses, and functional programming is just a function from requests to responses, right? So that was the original model, and it was a little bit awkward because it was hard to extend in the sense that you had to be upfront about all of the ways in which the language could interact with the system itself, which you had to embed as a data type. So monads sort of fixed that problem and made imperative programming something that was part of the design of the language from the go. So what is the history of monads? Well, monads are, you can tell from their name, they're clearly not made by like normal people. They're invented by mathematicians and part of category theory. So the classic reference here is Saunders Mac Lane, who basically founded category theory. He says something like, the recognition of the power and simplicity of the use of monads and comonads came quite slowly and started with homological algebra. And so he points to Mac Lane's work in '56, and so I dug that up, and here is the first description of monads in French. And if you look at it closely, this part of this paragraph is the only part that I can find that actually describes monads, which says, nothing to do with monads if you look at it, except it is exactly a description of monads if you understand homological algebra and you understand how these things are built up and something called the bar construction. But to the layman, this just looks nothing like what we would recognize as things. And again, what I'm trying to point out here is the refinement of concepts takes a long time. We had Landon with a textual description of denotational semantics, and then something like 5 years later, we've got Scott and Strachey turning that into a crisp formula that we can really parse and understand quite quickly. Here we have a description of monads, which is not only in French, but quite difficult to decipher, and yet does describe monads, but it takes some time before things advance. In fact, it takes Roger Godement to simplify things in this paper in 58. It's still in French, but it is understandable. I joke because I am French, okay? I'm allowed to say what I want. So here we've got the fundamental construction of things, and we can see that K, so this symbol, if only I could point K down here, has arity 0 to 1, which is return, and then P over here, I've made it bigger. P is join. And so here we have the join laws quite clearly written. So for years, monads were not named anything scary. They were simply called standard construction, and then maybe fundamental construction, and then they were just called triples for a long time because they consisted of some type T with some K and some P, and that was it. So they were kind of boring and not considered. So I think it's natural for me to ask the question, well, where did monads come from? Why are we using this word in the first place? And so with that, we have this chap, Jean Benabou, to thank. So in '67, he introduces a paper where he talks about monads more carefully. They are a play on the word monoid, but also they preempt polyads, which are a further extension that he's playing with. And so he says that the choice of monad actually comes from this example, and polyads are this extension. Okay. So how did we get here? Oh, we're trying to think about monads in the context of computer science. So how did we get category theory in computer science in the first place? So a lot of category theory started actually at IBM for computer science, where Samuel Eilenberg and Wright started thinking about automata in general algebra in terms of categorical constructions, and they use universal algebra and Levert theories to describe these things. Now, Levert theories are basically a way of describing operations and equations between those operations, which turns out to be a useful idea to this day. I think I'll probably skip through this. A little bit further on, in '71, Elgert starts thinking about monadic computation and iterative algebraic theories. So he connects Levert theories with Turing machines. So that connection to monads started in '73. And it's quite an interesting story how category theory really exploded in computer science. So McLean, in something like '70, talks to Goguen and says, well, maybe you should apply for this fellowship at IBM and spread some of the categorical ideas there. And so Goguen goes to IBM and forms a group called ADJ. They want to write under a pseudonym and create like a new foundation for computer science from the ground up, a la Nicolas Wu. If you don't know Bourbaki was a French mathematician who basically rewrote a lot of algebra in terms of universal constructions or simpler constructions. But the thing is that Nicolas Wu was not a person. Nicolas Wu was a complete invention of a bunch of mathematicians who wanted to write under a pseudonym. And so similarly, these guys wanted to write under a pseudonym, but for various legal reasons, I think we're just not far after Cold War territory. They weren't allowed to publish under like some random person's name. So they came up with this group name ADJ, which stands for Adjunctions, which was a terrible joke. But they write a paper called Adjunction, which is what they're named after, between computer science and category theory part 1, and then they had part 2, and they had I think 6 parts outlined on how this would go. And the project was huge and influential, but they actually never completed it. I think they never made it past part 2 of their entire thing. And so maybe that's another lesson from history for us to think about, which is it's really fun to start a great grand project and be like, oh, we're going to rewrite the whole of history, or we're going to rewrite the whole of this thing. But maybe we should just sort of start in small increments and just see how things develop. I'm thinking of Knuth and his wonderful tomes, but I don't know when they'll be completed. So yeah, they never made it past report 1 and 2, even though it was hugely successful, and Knuth's books are hugely successful. Perhaps there is something good in having a huge rewrite, but maybe you don't need to announce up front the next 15 chapters of your thesis. So where do we go from here? Oh, right, yeah. So the idea of category theory and what we call initial algebras, so proving uniqueness from syntax, comes from Burstall, who worked on structural induction earlier, and Thatcher, and they start thinking about algebraic theories and how they correspond to recursive functions. So they used monads to explain stateful programming. So they say we have a principal example, recursive monadic program schemes, which described are intuitively below, and then they carry on do the connections there. And then here we have sequential composition of programs corresponding to monad sequencing. So they know that monads are good for sequencing programs back in '75. Monads in the lambda calculus is kind of the next big development. So Dana Scott writes this paper relating theories of the lambda calculus, and he basically says, he asks himself, what is the theory of functions? And for him, the theory of functions themselves is category theory. And so he writes this paper, Eugenio Moggi picks this up in 1980 and says, oh, hang on a minute, we can use these ideas as a foundation of effects and computation themselves, and that happens in '88, where he talks about a lambda calculus which has things like state encoded into them. So side effects with state exceptions are all modeled with monads, but they're used as a way of modeling these features of the lambda calculus rather than as a means of programming. So as a means of programming, in '91, he writes another paper that shows that the notions of computation in programs, like partiality, non-determined side effects, exceptions, and continuations, can be modeled monadically. He doesn't actually sort of do programming. He just says that these programming features can be modeled that way. But for the story of effects as a programming feature, we go to '85, where Wadler is thinking about how you can deal with exceptions in a mathematical way. How can you program with exceptions in the first place? But he's not talking about monads. He's talking about using laziness as a means of capturing exceptions. I want to skip through this. In '88, although published in '90, Spivey picks up the theory of exceptions and says, actually, the way we do the functional theory of exceptions is by using monads. And so he introduces the maybe monad, and the words just and nothing are due to him in this paper. He introduces return, join, and bind, and shows how these are programming constructs that you can use. So that's what happens in '88. Wadler picks up on this idea. Oh, but before that, monads in programming continues. So we've got the work of Richard Bird, where he's thinking about how you can have a calculus for functional programming happening in '86 and '87 with useful properties. So these are properties that we would use quite often today. And then Spivey notices the connection between what Bird is doing in category theory in '89. And then, so he continues to use monads as the underlying, or he conjectures that monads are a good way of dealing with the underlying theory. And he's not wrong, and he ends up sort of having a construction that's close to what we call the free monad, which we would use today to describe syntax. Okay. So for monads in Haskell as popularized today, we turn to Wadler, who wrote a really important paper in 1990, which was sometime after, a year after the introduction of monads by Spivey. And what he does here is he introduces a whole bunch of really useful examples that show you how to use monads in programming. So, and the point that I want to make here is that although the ideas were kind of already there, that wasn't the end of the research, right? It was just the beginning of things. Wadler then took those ideas and showed you how to actually use and apply these things. So there is a lot of value in just explaining something that you feel is sort of obvious. I think Spivey knew how to do all of these things, but Wadler actually popularized that and made it really important for us today. Okay, I'm quickly running out of time. I think it's...
You can have an extra 10 minutes
Wow. Okay. Okay. I will try to. I will wrap quite quickly. So, monad transformers are the concept that we would use today to write things, and type classes were introduced by these chaps in '89. They led to constructor classes. I think I just want to whiz through this and just sort of tell you that, again, it just took a long time before we got to the point where we could actually use monads as a programming concept that we have today. But the problem has always been modularity. I wanted to pick up on do notation, which was, again, first given by Launchbury, where we would be writing Haskell with curly braces and semicolons to do imperative programming. But the actual implementation was by Jones in '94 in a language called Gopher, which was one of the early Haskell compilers. And for lexical reasons, he introduced the do keyword to make things work out, which I'm kind of sad at. I preferred the non-do version of Haskell, but there we are. As I said, do notation is syntactic sugar. Syntactic sugar was a term invented by Landon, as was indentation-sensitive languages. The last time I gave this talk, this slide didn't exist because I did not know where the origins of bind came from. But thanks to the internet, somebody very kindly posted on Reddit that there was a post on Twitter. So thank you, Iceland Jack, for pointing me to this post on Twitter, where Andrew Gordon said, 30 years to this day, he submitted his PhD thesis, and the bind symbol is the longest-lived survivor. So perhaps the lesson for us here is that although your PhD will be, born out of sweat and blood and years of sweat and blood, maybe you'll have a contribution as tiny as 3 characters. But actually, that is not the purpose of the PhD. The purpose of the PhD is to grow you rather than to make an impact on computer science. Some do bigger than this, some as much as Andrew Gordon's 3 symbols. So here's a copy of his thesis. Here is the first use of bind that was published, and he says that comes from where you think it does. He'd been using this right triangle, which is how I was taught bind as a symbol, through some earlier work in '89. And here we have what I would call the free monad for concurrency, but that's not what he called it. He just used it as a data structure. And he saw that it was easier to type right than triangle, and he wanted right equals to mean bind because there was something to do with equality going on there. Okay, so that's where that came from. And I want to just wrap up with effect handlers, which is the stuff that I do, which basically says that syntax and semantics are the way that we should give is the way we should program with effects. And so I'm just going to whiz through this very quickly. I don't expect you to understand actually much of this talk at all. But the syntax, so the idea is that we start with the syntactic programs, which are basically trees, and we can handle those into expressions that evaluate those trees. So that's denotative. And why do we like them? We like them because the operations are algebraic. They have nice properties. They're extensible. You can add things to them. They're modular, which means that you can handle things over and over. They're flexible. And there are multiple semantics that you can give. They're equational, which means you have some systems of equations. They're pervasive. They're absolutely everywhere. And they're efficient. So there are lots of reasons why I like these things, but I'm not going to go into any of that. They are based on these things called Levert theories. Levert theories go back to universal algebra. John Power picked up on this idea and thought, well, it's good to do operations and semantics in that way. Plotkin and Power go into algebraic operations, and eventually we have Mattia Pretnar, who was a PhD student working with Plotkin, and he invented algebraic handlers, or handlers of algebraic effects. And then we get into like where we are now. So after that PhD, a whole bunch of things happened. And so now the bibliography since, and notice this since 2009, is quite enormous of things that we could possibly cite. And so, that's where my research starts. We've got higher order effects coming into play. And really, some of this is interesting because it was me meeting, it became important when I met somebody called Rob Ricks at ICFP. He was working at GitHub, and he was saying, well, we're using algebraic effects, but things aren't really working with everything. How can we make it work? And I said, sounds like what you need is scoped effects. And so I showed him some of the work that I'd been doing with some co-authors. And the idea is that although you have effects, sometimes you want to interpret your program in multiple ways. So you might have like a non-deterministic program that you do depth first, breadth first, or depth bound, or you maybe just want one result. But these depth first, breadth first, depth bound, and once are normally treated as handlers in the effects world. And I thought, well, it'd be useful if these were operations in their own right. The point is that we wanted to abstract those into some kind of syntactic construct called search instead, and that became the idea of higher order effects. Where are we going with this now? I don't think I really care about you understanding a bunch of equations. Let's carry on through this. I showed them that work. They were worried about efficiency. That was something that I had also written about. And it was 250 times faster than the previous attempts that they had. And so they shipped it. And that's what GitHub used for semantic analysis of lots of programs that you'd submit. OK. I think this is the conclusion. Oh, yeah, right. So there are now a whole bunch of effect libraries, which we can just whiz through. I think the state of the art is that there are lots and lots of different implementations of these, none of which are ruling. So to conclude, we've seen like a whole bunch of history that I've summarized very badly, starting from 71,000 BC. What I hope to show you is that the development of computer science has been long and arduous, and hopefully you can be part of that. So what next? Well, I think that's a question for you. So good luck with your PhDs, and I hope that your research goes well. Thank you very much.
Thank you, Nick. I think we have time for a question or two.
Hi, first of all, thank you for the talk. I just want to ask, if you have anything to say about how we can kind of balance looking to the past and through all of these ideas that you showed to us versus just new ideas and
yes.
How much should we be looking to the past versus?
Okay, you're asking me after this how you should balance looking into the past. And I say that sort of almost seriously. So as a PhD student, I would love digging into the old historical references to stuff and just getting utterly lost in what is an absolutely vast literature. I think that was a mistake. It makes for fun talks. But I think that I would have been better off focusing on just my own ideas and developing something that I thought was cool now. And it took me a long time to recognize that. I didn't need to understand all of history before I could make a contribution. So I think that my encouragement to you would be, when you've got an idea, almost always that idea will be novel enough. And once you work on it and develop it, you should be aware of the literature a bit. But I think when you're exploring, just understand your own idea well. Then, as you're understanding that idea, start writing a paper about it, start doing a literature review, and then you'll think, oh, that connects to this. And with almost every PhD student I've met, they think they've been scooped. And actually, often the case is, yes, that there is related work. Thank goodness other people have had that idea or similar. But actually, you can probably extend and change and develop or have your take on that idea. Or there's almost always something different that you can do. There's always a different take on things. I think research is extremely fractal. So you've got the big broad strokes written in the 60s and 70s, and since then we've been refining those strokes as we go. And there seems to be no end to that. So I would say, be cognizant of history. Make sure you make sure that you refer to things properly. That's really citation is essential. But don't be afraid to just pioneer into your own research and be a little bit blind to what's going on for a while, and then sort of emerge and then have a look at what people have done.
It's just one thing was, I guess you mentioned sort of algebraic effects, and you mentioned that, say, GitHub rolled that out to production. So, how long did it actually take from, the first? So, I think it probably came up, but it was went through very fast.
Yeah.
How long did it take from, the first, I guess, theoretical proposal of algebraic effects to the first actual industry deployment? Because I know there's huge variance in how long it takes these ideas to trickle down from academia to industry. What speeds this up? What slows this down?
Yeah, that's a really good question. I think it took quite some time. I think it depends on exactly what you're asking. So I think my work on this stuff was in 2014, and then the chat with Rix was maybe 5 years later. and their implementation was basically started as a copy-paste of the stuff that was in my paper, and then they engineered it amazingly well to make it work. But I think that engineering took them a few months of production, or maybe I think he had initial version in 2 weeks, and then they worked on it for a couple months after that. So that part was extremely rapid. But the actual point at which they started using it, that took a long time, to actually go in. So yeah, I don't think, despite what grant writers kind of make us do, I don't think we should care about impact in industry almost at all. Initially, I think we should just be interested in interesting ideas and things that work well, and then let industry catch up. They don't be over focused on reaching out and trying to make contact. But I mean, what do I know? I'm not very good at this. So I think the ideas are more important than the industry. Yeah.
All right, let's thank our speaker.